Hello, I'm Tyler Hutchison, a signal conditioning design engineer at Linear Technology. Today I will be talking about driving high-resolution SAR ADCs with the LTC6363. Driving high-resolution SAR ADCs like the LTC2378-20, a 20-bit 1 megasample per second ADC, often requires trade-offs between power consumption, linearity, and noise. These parameters are dependent on the driver, the interface filter, and even the ADC topology itself. The LTC6363 can drive up to 20 volts peak-to-peak and exhibits excellent THD and noise with a small amount of power, which makes it well-suited to drive many precision SAR ADCs. In order to achieve datasheet specifications of the ADC, first off, the amplifier needs to be able to drive the ADCs to their full-scale value. For SAR ADCs like the LTC2378-20, a full scale is often 10 volts peak-to-peak. But with the 2338, it can be as high as 25 volts peak-to-peak. However, with differential outputs and a supply up to 11 volts, the LTC6363 can drive all of these ADCs up to 20 volts peak-to-peak with no penalty to distortion. Additionally, the low distortion and high SNR come at little detriment to power consumption. Many amplifiers with similar specifications burn significantly more power than even the ADC to achieve 20-bit performance. After these quick considerations, the designer must pay close attention to the interface between the driver and the ADC to achieve full system specifications. In SAR ADC applications, the typical interface filter is an RC filter with a differential capacitor and two common mode capacitors. This filter serves two primary purposes. First, to band limit the noise of the amplifier and the resistors. Second, to isolate the amplifier outputs from the charge kickback from the ADC, which occurs whenever the ADC switches connect the sample capacitors to the rest of the circuit. Without a carefully designed filter, this sample event can cause significant distortion. Before I demonstrate this, let's first look at band limiting noise. The LTC6363 has 2.9 nanovolts per root hertz of wideband noise. After including the noise of the input and feedback resistors, the overall wideband noise is 10 nanovolts per root hertz. Using linear SAR ADC, the LTC2378 has a signal-to-noise ratio specification of 104 dB. Comparing this SNR to the driver noise is arbitrary unless we specify the bandwidth of the filter between the driver and the ADC. For example, this is a plot of the system's SNR when the LTC6363 drives the LTC2378-20 with 1K resistors. Even with a 1 MHz RC filter, the SNR only drops by 1.2 dB to 102.8 dB. When the LTC6363 drives the LTC2338, the 100 dB SNR drops by only 1 dB to 99 dB at a filter bandwidth of 8 MHz. This trade-off between bandwidth and SNR can be estimated for a number of Linear's precision ADCs. Clearly, the amount of deterioration depends on the filter, the amp, and the ADC. Of course, if the signal is being oversampled, then additional digital filtering can also increase the signal SNR without further adjusting the RC filter. This will be useful to remember in the next step as I demonstrate the system distortion versus filter bandwidth. Theoretically, the filter bandwidth could be decreased to whatever SNR we wanted. Severely reducing the filter, however, can seriously affect system distortion. When the ADC input connects to the sample capacitors, there's a brief glitch when charge sharing occurs among the driver's output capacitance, filter capacitance, and the ADC capacitance. If this charge doesn't completely settle out, then distortion will take a significant penalty. The distortion of the LTC6363 when driving only a 1.3 MHz filter with a 2 kHz signal is minus 111 dB. However, when the LTC2378-20 is added to the system, the distortion deteriorates. If the ADC glitches are responsible, then reducing the sample clock should improve the THD. This step will allow for the amp output to settle more completely. When I reduce the sample clock in half, the THD numbers do return to acceptable levels. From this observation, there are a few directions to go. First, I can reduce the clock speed. Second, I can accept poor distortion for better SNR numbers. Third, I can open up the filter bandwidth to reduce the filter settling time. This may reduce SNR, but that can be corrected with digital filtering. Increasing the filter bandwidth to 13 MHz results in great distortion numbers, but SNR drops to 94.6 dB. Fourth option is to choose a bandwidth and vary R and C values to increase THD numbers by trading off driver loading and charge sharing with the ADC. This behavior is difficult to predict in simulation and best determined empirically. For instance, by sweeping component values, we can achieve minus 110 dB THD at 2 kHz with this 500 kHz filter. The LTC6363 is capable of maintaining high accuracy of our most precise ADCs with little additional system power. By paying careful attention to the interface filter between the driver and the ADC, system designers can optimize for distortion and THD based on component values, sample rate, and SAR input topology. Please visit us at linear.com for more information. Thank you.